Well, sorry for all of the interruptions. Looks like the splitter wasn't working very well with my computer. So, my name is Feng. I'm from Carnegie Mellon University, and I'm giving this talk for our group working on working with blue waters to simulate the first galaxies. So our group, the PI is Tiziana Matteo, and I'm a student of Rupert Croft, who is a co-PI. And there are two postdocs also working on this project, Nicholas Petascale, an expert on reionization, and Nishi Kandai, who's an expert on running large-scale simulation with full machines. And Volker, who is the author of the main author of the code, the architect behind the simulation code we use. So also I would like to express my thanks to the team, the staff team at NCSA, especially our contact, Mark Straka, has really been very, very instrumental and helpful for us to getting the simulations running. So here on the right, I'm showing a picture of the initial condition and our first a slice and a piece from our first snapshot we've taken. So this is from one of the process, but we have 45,000 of those little slices. So so the general line, the outline of the talk, I'm going to talk about basically 5 things. So why is the problem we are solving interesting, and also what is the problem we are solving, and what are making these problems challenging, and why do we want to solve it in blue waters, and what is the current progress, what progress we made, and a brief what's the word for it? A brief speculation towards the future. So, as Brian may have already have an introduction to cosmology and astrophysics, so I'll keep this part short. So in general, cosmology, the problem we are trying to study, is a study of the universe as a whole. So we have 2 main questions to answer in cosmology. The first is what is the universe made of? The second is how does it evolve? And it turns out the components of the universe is mostly unknown to us. So about 70% of it is dark energy, which we know almost nothing about. And about 25% is dark matter. We know they interact with gravity, but that's pretty much all we know. The part we know very well is the baryon, or ordinary matter, which makes up all of us and everything we use every day. So we know that part very well, but that's only 4% of the universe. So the study of the universe is, however, when we look at the evolution history of the universe, we have a pretty good picture. So we have this standard model of cosmology, and it has been working very well over many years, being able to explain most of the observations. So the history of the universe is roughly can be described with this figure here. So the universe started from the Big Bang, and then there is a period of dark ages, which is relevant to our study. So in these dark ages, the atoms in the universe are neutral. Therefore, they absorb light. And also the universe is dense and uniform. There are no structures, there are no stars, no light sources. In the dark age, the universe is literally dark. At the end of dark age, the first galaxies formed, like what Brian has talked about. The light from the first galaxies will ionize the neutral hydrogen in the universe, and eventually, towards the end, so that marks the start of the epoch of reionization. So at the end of reionization, most of the hydrogen in the universe is ionized. Well, atoms in the universe is ionized, and the universe becomes pretty much similar to what we see today, transparent, and the photons can travel pretty much freely for very large distance. So the dark ages are becoming a new frontier in the universe. So we really know very little about the dark age. Well, the end of the dark age, and that's because we don't have the instruments to do the detection, to do the observation. But this is going to change very quickly in the next decade or so, because many multi-billion-dollar telescopes, both ground-based and in the space, are going to be probing the first light from the first galaxies with very, very sensitive infrared sensors. So that's a multi-billion question. So, but, well, that's how it goes in observation, but how are we doing about the theory? It turns out we're not doing very well with the theory. So we can do pencil and paper work, but it is only up till now with blue waters we can actually start doing first principle simulations of the first galaxies from a uniform volume. And the reason is because these galaxies are small. They are rare and small. So because they are rare, we need a huge volume to sample them. And because they are small, we need simulations with very high resolution so that they are actually resolved. The structure of these galaxies are resolved in the simulation. So therefore, we propose to run this. Therefore, we run this blue tide simulation. So it's a simulation designed to resolve the first galaxies in a large volume. So the size of the simulation box is about 400 megaparsec. That's a terminology we use in cosmology. In like a human units, it's about a few billion light years. And the resolution is about, well, it's about a few hundred light years. So what's remarkable about this simulation is it's big. We do embody gravity for dark matter, and we do hydro simulation for ordinary matter, and we have about 700 billion particles. That's about 0.7 trillion particles in these simulations. In terms of mass resolution, that gives us a 12 orders of magnitude in mass resolution. So, but how will galaxies look like? How do galaxies look like in this blue tide simulation? So, how do we form these galaxies actually? So we start from initial condition based on the cosmic microwave background, which is measured like to 1 part out of, I believe nowadays 1 part out of 9 or so, very precisely measured. So these initial fluctuations will generate an initial condition from a realization of the microwave background. And then, well, this initial condition, this is actually the real initial condition we're using for the simulation. It's 400 megaparsecs size, and the size of the data set is about 15 terabytes. So from this initial condition, we evaluate with physics with our simulation code framed by Volker. It's a Gadget, amazing code. And then eventually we're going to produce these mark images of the first galaxies. So these guys, we got it from a simulation with the same resolution, but with a 60 times smaller box. But with blue tide simulation, we're going to get roughly 6 times more of these galaxies, so we can do statistical studies on these galaxies. So the physics goes into this simulation are I summarized them with 4 major pieces. The first piece is gravity. Second piece, hydrodynamics. Third piece is the feedback of star formation. The last piece is atomic physics for cooling and producing the star-forming materials. It turns out all of these pieces are massively parallelizable, and they scale fairly well with the number of mass elements or particles in the simulation. So for gravity, we use a tree PM code. We use the tree PM, so short range with the tree lookup and large range with the accelerated the fast Fourier form transformation. The hydrodynamics is totally local, so every particle talks only to its neighbor, so it's on the order of number of particles. The star formation feedback, they are just the sources and the sinks in the density field, so that's also trivial. And the atomic physics, we use iterative ordinary differential equation solver, so that's independent for every particle, so that's also massively parallelizable. So what are the challenges then? Well, the simulations are big. We need a large volume, high resolution. We have 700 billion particles. That needs a lot of memory. We actually have to run the simulation on full machine. Well, technically speaking, it's 90% of the machine of blue waters. So in order to accommodate all of these particles safely in memory. And also with this many particles, we have to use a lot of CPU power to calculate them, and a lot of communication because they still have to talk to the neighbors. And when we are finally done writing out snapshots, That's a huge burden to the I/O system. So after compression, each of our snapshots is 20 terabytes in size. And we are planning to take 20 of them. And a restart file is about 300 terabytes. So, well, another challenge is to comprehend the result from this simulation. So we've been working on like visualization of the simulation with a tool, GigaPan. It's a service to create and share high-resolution, large gigapixel images. Well, actually, our simulation, so this was one of our previous largest simulation, which is an order of magnitude smaller than blue tide. We made a trillion pixel image, and we can visualize it. Well, we can use their service to just load up the browser and browse this image in real time of the simulation. So with another simulation, Massive Black 2, which has the same resolution of blue tides but in a smaller box, we actually built an interactive tool to explore the galaxy catalog in the simulation. So we can jump in to any location. We can jump in to select a halo or select a galaxy and jump to the location and look at how it looks like, both, well, the gas component and the stellar components look like. So how do I do with the time? All right. So, well, then I'll see if I can show you how this works. So this is so we jump to, let's go to a lower redshift. We can jump to Halo 0. See, it's working a little bit to get all of the stuff from the server. Well, now we are here. And we can, well, so the immediate galaxies in this region are all shown, and we click on one of them, we can see its properties from the simulation of the property, the properties in the simulation. And then we can also look at the stellar components, how they look like. And it's pretty, well, it's an interesting tool. We can look at the morphology of the galaxies from the simulation directly, and this is a data set of about about 2 terabytes of data in this image. So, all right. So let me Windows. Right. Okay. Let's go back to the main course. So we have some tools to, well, so for blue tides though, we really have to blow this technology to like 1 or 2 orders of magnitude bigger. So we are still working on that. Okay, so why do we run the simulation on blue waters? Why blue waters is the machine for blue tides? Well, because blue waters really is the only machine that can accommodate this simulation. So blue waters has 1.6 terabytes of memory, petabytes of memory, and this memory is crucial, it's very instrumental for us to run the simulation. So, and also, what's more important is blue waters, when it's designed, it kept in mind to keep all of the components of the system balanced. So that turns out to be very, very helpful, because when we write out these snapshots and restart files, we really don't want to waste so much time just to write those things. And also, when we are having the communication, we also don't really want to waste a lot of time doing the communication. So comparing blue tides on blue waters with our previous simulation, Massive Black at Kraken, we see it's really a simulation an order of magnitude in every aspect. The number of CPUs, the number of the total amount of memory, and then the size of snapshots, and the size of restart files. But even though the simulation on Kraken is smaller, we couldn't take restart files because of I/O bottleneck. Okay, let's go down. So the simulation, the hydrodynamic simulation with SPH has really been going up. The size of this simulation has really been going up exponentially with respect to time. And so our most recent last 3 simulations are here. They are all on the order of beyond or on the order of 10 billion particles. And so we are really trying to keep the size of the simulation in sync with the size of the machines, and that's a lot of work. So the code we're using is based on Gadget, originally written by Waters Symposium. It has all of solvers for all of the physical processes. But for running on Blue Waters, we really did a lot of improvements to the code. We implemented a bunch of new physics models. We hugely improved the threading efficiency, and that's important because Blue Waters has about 16 integer cores per NUMA node, while the previous code running on Kraken, it only has 6. So we really had to improve the threading efficiency. And then, well, we are also, if you look at the number of lines we touched, we are doing more with fewer lines of code. And that's because we are in the process of cleaning up the code and doing a release of the code for doing petascale, highly scalable Gadget's smooth particle hydrodynamical simulation. So the physics, well, we have these physics because I'm running out of time. I'm not going to talk about them in detail, but I want to mention the news. One of the important pieces is the pressure entropy formulation of SPH, which solved many of the troubles that's been haunting smooth hydrodynamic simulation for decades. So, but the trade-off is we have to use 4 times more computation resource, well, in terms of CPU time, to run this pressure entropy simulation. And so here we are looking at the threading efficiency improvement in the threading efficiency. On the left side was the old code and the number of threads versus the wall clock time for doing, I remember, was like 10 time steps for a test case. So you see, it really, the solid lines, colored solid lines are the threaded components of the code. And you see, we really are starting to be hurt after more than 10 threads. But with the improvement, well, we can pretty much go pretty well on the order of like 16 threads. 16 threads is here. We're still doing very well on 16 threads, but starting to get hurt at 32. So that's because, well, even though the components are threaded, they are not fully threaded. They are still like linear parts, sequential parts. So, well, the way we make the threads faster was to observe a simple fact. It's because, well, that is in the old code, we have to protect the particles as the threads update the particles. We don't want 2 threads update the same particle. But the old way was saying we don't want any threads to be updating any particles at the same time, which was a reasonable thing to do because then we only require 1 global critical section to protect all of all of the particles. Well, but that's causing this huge efficiency because you see, if thread 1 and 2 are not updating the same particles, they still have to do this sequentially. So, however, in the new code, we are using 1 lock per particle, a spin lock per particle, and therefore, if 2 threads are not updating the same particle, saying updating thread 1 updating particle 1, thread 2 updating particle 2, well, they can do it simultaneously. And the good thing is, we know with a very large domain, threads are very unlikely to be working on the same particle. So probabilistically, the collision scenario here is never going to happen. So the threads are now probabilistically fully parallel. So here I'm showing you some of the timing information we got from the current runs we are running on Blue Waters. Comparing this, well, I put this on top of a chart of an old scaling test we did on Kraken. And you see the new simulation, the hydro part of the simulation, is as expected, it's slower than the old scaling test. Well, so I also have to mention I've scaled these numbers so that they roughly are having the same load. Well, you see the hydro is a bit slower because we are doing 4 times more computation. And once we take that into account, it's actually 2 times faster because of the threading, improvement in threading. So, and then the tree part of the gravity, it's also doing pretty well. It's roughly on the same order of the old benchmarks, old scaling tests we did. The only issue we are currently having is the particle mesh, and we are still working on that. We're still working on that to bring this really down back to where it should be. So I'm running out of time, so let me do a quick summary. So basically, I'm trying to convince you that cosmology simulations are, by nature, supercomputing problems. That's because the universe is infinite, and we care about different scales. We always want to resolve to small and small scales to look at rare objects and resolve them. So whenever there are bigger computers, we will have very good problems to run on those computers. And the second point is the physics of the cosmological simulations are very standard. They are very well understood. We have very much well-developed algorithms to run these simulations, and they scale very well. So we don't need exotic physics. We don't need exotic states of matter. We don't need solve stiffy ODEs or differential equations. It's just a regular thing. So it's proven technology. And all we need to do to simulate the universe is to bring the big computers and the scalable softwares together with hard work, and then we can make our science proposals into reality. All right.